Hello everybody. In previous video I have covered introductory topics on layer 2 switches, how they learn MAC addresses, how they run spanning tree protocol for in default mode for all VLANs, etc. In this video I am going to tackle parallel spanning tree protocol or parallel spanning tree plus protocol, which works both over 802.1q trunks as well as Cisco's ISL interswitch link type of encapsulation. So let's go. Let's recall what is STP priority vector. Well, STP priority vector is a set of 4 values, ordered set of 4 values, starting with root ID, then root path cost, bridge ID, and port ID, where bridge ID and port ID pertain to the neighboring switch that has sent configuration BPDU. Initially, in the whole switching domain, it's only a root bridge or switch that generates and sends out configuration BPDUs, and all other switches receive those BPDUs, recalculate the values except of the value of root ID, and send out the updated configuration BPDUs in the so-called message priority vector. Message priority vector is the same ordered set of values: root ID, root path cost, bridge ID, port ID. Bridge ID and port ID of the sending side. And there is also a notion of port priority vector. This is the same ordered set of 4 values that are stored for each port. So when port receives spanning tree message priority vector, the values from message priority vectors are compared to the values of port priority vector stored for the port that has received configuration BPDU. And provided we have a stable topology, no recalculation is made because everything is pre-calculated earlier, so nothing entails recalculation. But in case spanning tree message priority vector is superior to the port priority vector, then the port priority vector values are replaced from the values from the message priority vector, and recalculation begins. While in case of spanning tree message priority vector being inferior to the port priority vector, then the switch sends out its own port priority vector as a message towards its neighbor that has sent inferior spanning tree message priority vector. Classical spanning tree protocol runs single instance of spanning tree for all VLANs, which means some interfaces are going to be blocked for all VLANs. There's no way to use layer 2 traffic engineering or configure traffic engineering with classical spanning tree or single spanning tree or common spanning tree, as they call it. But this protocol is very slow because, well, you will see those timers for a delay timer and the recalculation of the port role. Cisco's solution is parallel spanning tree plus. This is not a solution that speeds up the operation of classical parallel spanning tree protocol, because each parallel spanning tree instance, parallel spanning tree plus runs single instance for each VLAN, a separate instance for each configured VLAN, which means that all VLANs get their own spanning tree instance. With default configuration, all VLANs will have the same topology of their spanning trees, which means no layer 2 traffic engineering. But still, you have an option to configure different root bridges for different VLANs. And thus, you can influence the topology for the instance of specific VLAN, thus achieving layer 2 traffic engineering. But still, parallel spanning tree plus is based on the classical spanning tree algorithm and is very slow. Let's see how the how priority field is redefined to support parallel spanning tree protocol or parallel instances of spanning tree protocol? Well, the initial priority field contains 16 bits, which gives us 65,536 or 2 to the power of 16, starting from all zeros and ending with all ones. And we also have system MAC address, which is basically the base MAC address that describes the switch itself or identifies switch itself. These two values constitute bridge ID and root ID for the root bridge. Now, for parallel spanning tree, the priority field is redefined as follows. 4 most significant bits are set aside for priority itself, which means that the least significant bit of the priority field has the weight of 2 to the power of 12, right? Because we are counting from right to left, from the least significant bit to the most significant bit. So bit number 12 has the weight of 4096. Now, for parallel spanning tree version of STP protocol, we have to change priority field with steps of 4096 units. The least significant 12 bits contain the VLAN identifier and are called extended system identifier. Extended system identifier can be thought of as the extension of the physical switch, because if this field we concatenate with system MAC address, we get the virtual identifier of the virtual switch containing 48 bits of system MAC address and 12 bits of the VLAN ID. It's kind of, if you configure 5 VLANs on your switch, you get 5 virtual switches, each having extended system ID plus system MAC address. Plus means concatenated here, not numerically plus. So, but this field, I mean extended system ID, is counted in calculation of the total priority of the switch in the given VLAN. How it's calculated? Well, the VLAN ID is added to the default or manually set priority field. For example, default value of priority is 32,768. For VLAN number 1, the total priority for VLAN number 1 is 32,769. For VLAN number 10, it's 32,778. For VLAN number 100, it's 32,868, etc. Well, since we are talking about VLAN ID, let's introduce VLANs. Imagine the possibility that engineer does not leave its desk and can place any end-user device in a separate virtual broadcast domain. This is the aim of VLANs. VLANs use tagging. Tag unambiguously identifies the source broadcast domain in which this or that frame was instantiated initially or generated initially. For example, here in this slide we have 2 broadcast domains and they are virtual. So red broadcast domain contains Macintosh and hosts, and the light blue broadcast domain contains the workstations. So in order to preserve identification of the initial broadcast domain where the frame was sourced, from which the frame was sourced, there must be some way to carry this identification alongside with each Ethernet frame. For this purpose, we have 802.encapsulation or a 2.1q protocol. Well, initially it was a separate standard, but now it's part of 802.1d. This is basically not pure encapsulation because no one adds a new header containing new source and destination MAC address fields as well as some other fields. It's only a 4-byte field, 802.1q or 802.1q tag, that gets added to the initial Ethernet frame header carrying user payload. Now, this field, these 4 bytes contain the following subfields. First comes TPID, which stands for Tag Protocol Identifier. It contains the value of 8100 hexadecimal and points to the structure of the data coming after this field. So, provided this field contains 8100 hexadecimal, the next 3 bits are priority code point, which encode layer 2 quality of service marking, which is used in case you implement quality of service in your network, and in case of congestion, different classes of your traffic marked with different values of PCP can be serviced differently. You set aside some priority traffic or traffic classes for which you provide more bandwidth, and some classes get less bandwidth. Next comes DEI, which stands for Discard Eligible Indicator. If set, this frame can be discarded provided you have congestion in your network. And the last 12 bits contain the VLAN ID. So regarding ports on switches can be divided in 2 large classes. First class is access ports. These are the ports that receive frames from the end user device. Primarily, the frames from the end users are native or untagged, and thus each access port have the configuration parameter, which is called PVID, Port VLAN Identifier. This is configurable, but default value is PVID number 1. So basically, all ports of the new switch that you have unboxed are in VLAN number 1 and implement only one broadcast domain. But you can configure, of course, you can configure access ports into different VLANs, and so when native Ethernet frame comes into such port, or is received by such port, it gets tagged with the VLAN tag or VLAN identifier equal to the port VLAN ID. There are also trunk ports which carry tagged Ethernet frames with VLAN identifier inside them, inside the header of the Ethernet frame. So a couple of words about how switches calculate port roles. Suppose we have some topology change, as in this picture. The left leg between root and switch D21 gets broken, and we use optics for all 4 spans. So in this case, the root port on switch D21 does not go down, because this is a media converter from electrical to optical, so the port stays up. But obviously there is a topology change. So the port stays in its current state for 20 seconds, as well as all other ports in this topology, including this one, which is blocked and which is blocking this connection from C11 to A11. Basically, A11 is separated from the root bridge, as well as D21. From one leg, it's separated by the break of the fiber. On the other path, it's separated by the blocked port. So 20 seconds is max H timer, and the ports stay in this state until this timer expires. Then they go to listening state, which is 15 seconds long. In this state, ports discard user frames, and the switch calculates the new topology. For example, switch D21 does not hear from the root bridge, but after 20 seconds, this switch it is constantly receiving BPDU frames from the root bridge via D21. So this one, A11 switch, starts sending its own BPDU, not its own, but the BPDU frames generated by the root switch, and recalculated fields like bridge ID, root path cost, and port ID. So it starts sending them towards switch 21, D21, in this listening state. So every switch starts to hear from the root bridge over backup paths. And then the switch, for example, D21, recalculates topology and understands that now the position of the root bridge is not behind the upper interface, but from the lower interface, behind the lower interface, because it didn't hear from the root bridge for 20 seconds through the upper port. So basically, this port, lower port of D21, assumes the role of the new root port. And also, this former blocked port becomes listening and then learning, because A11 hears from the root bridge only through its right port, not through the left port, right? Because here we have a fiber break. Learning state. In the learning state, each port discards user frames but learns MAC addresses. So basically, the switch learns MAC addresses in advance before the port is going to forward the user traffic. And then after 15 seconds in learning state, corresponding ports transition to forwarding state. So basically, the final state here is that this port becomes the root port, this port becomes the designated port, but connected to the broken segment. Ports on the root bridge stay designated for both connected segments. Here, root port continues its role of root port, because nothing changed here. Here, D21 has, probably here is D22. Okay. So this stays as designated port, but this one becomes root port, and the left port on A11 becomes the new designated port. Now, if port was initially disabled with no shutdown command, and you've connected it to the switch and enabled, it spends in blocking status quite short amount of time, then transitions to the listening state, where it spends the next 15 seconds according to the classical STP algorithm. In this state, switch decides if this port must be brought back to blocking state or promoted to the forwarding state. If switch decides that the port must be promoted to forwarding state, then after 15 seconds spent in listening state, the port spends next 15 seconds in learning state and then transitions to the forwarding state. So here we have total delay of 30 seconds. Well, this is a notion of indirect failure, and here we have basically indirect failure, right? Because when the failure occurs, our ports stay up and active. So this is indirect failure, and every time we have indirect failure, we must calculate or count down our timers, like max age and other timers of other protocols. So let's configure our VLANs in trunks. Thanks for watching. Now, if the port was initially disabled with, for example, shutdown command and is enabled, it spends in blocking status quite little time and almost immediately transitions to the listening state, where the switch calculates the future role for the port. If the switch decides that the port must stay blocked, then the port is returned to the blocked state and the topology doesn't change much. But if the switch decides that this port must be promoted eventually to the forwarding state, then the port is promoted first to learning state, where it spends another 15 seconds learning MAC addresses but not forwarding frames, and then is promoted to the forwarding state. So in this case, we have total delay of 30 seconds, twice forward delay timer. Now let's configure VLANs and trunks. It's a good practice to check current configuration before introducing any changes. So let's check what VLANs are configured on our switches. Show VLAN brief. This command gives concise output about VLANs configured on the switch as well as ports assigned to the specific VLANs. As you can see, there's only one default VLAN, VLAN number 1, and all the ports are assigned to this VLAN. So basically each switch, new switch, implements only one broadcast domain. And this is the same for all the switches on the diagram, including the distribution switches. Okay, now let's see the status of the ports. As you can see, for access layer switches, specifically for switch number 1, there are two uplink ports, Ethernet 0/0 and 0/1, that are connected to two distribution layer switches and that are in status connected. If we check the status of the ports, we can see that indeed physical layer is up and line protocol is also up on these interfaces. But what about trunking interfaces? There are no trunking interfaces on any switch. Let's verify, for example, on switch 4. Show interface trunk. Show interface trunk. There are no any trunking ports or interfaces on any of the switch, including distribution layer switches. What about VLANs? Show spanning tree. Currently only one spanning tree instance for VLAN number 1 is calculated and has the active topology here. We can see that the root bridge for VLAN number 1 is behind Ethernet 0/0 of switch 1. If we check show CDP neighbors, okay, Miss Tipo, show CDP neighbors, we see that behind the local Ethernet 0/0 interface of switch 1 is indeed switch 6. Now let's add new VLANs. For this we must go to the global configuration mode and use the following command. VLAN 5, and let's give it a name, for example, engineering. And now VLAN, for example, 10, name finances, and VLAN 11, and name directorate. Okay, so now I have saved the configuration and let's check show VLAN brief. We see that 3 new VLANs have been added to the output of show VLAN brief, but no interface is assigned to these VLANs, because we didn't assign them manually, and by default all interfaces, as you can see here, are assigned to VLAN number 1. As soon as we configure trunk interfaces, some of the ports like Ethernet 0/0 and 0/1 on switch 1 will disappear from VLAN 1 assignment, because these will be trunking interfaces and hence they will be forwarding frames of all VLANs. So they will kind of belong to all VLANs that are allowed through via trunk interfaces. Okay, let's replicate the VLAN configuration to all other switches. So the configuration of VLANs is stored in VLAN.data file. Let me find it. Dear all file systems. VLAN.dat 00001. Okay, so let me just do show history and just copy paste from here, and I will replicate this to all other switches. I prefer manual configuration. I don't like using VTP, virtual trunking protocol, to exclude some dependencies on, well, some external conditions, so to say. Okay, switch 4. Switch 5. Switch 6 and switch 7. Now, let's check spanning tree for the VLANs. Show spanning tree. Well, we can see that there is still only one VLAN and spanning tree instance for VLAN number 1. Why? It's because we don't have trunk interfaces, and all other interfaces are by default assigned to VLAN number 1. So basically there is no interface in VLAN number 5, 10 or 11. Let's check it. Show VLAN ID 5. We can see that there are no ports in this VLAN. It's rather here. VLAN 5, name eng, engineering status active, but no ports. So let's configure trunking interfaces, but let's first configure them on switch 6 and switch 7, as they are the distribution layer switches. Basically, we can configure all these interfaces, Ethernet 0/0 through Ethernet 1/2, in a one go by using interface range command 0/0-3 Ethernet 1/0-2, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 interfaces, and let's configure them. The commands to configure trunking in trunking mode here are as follows. Switch port. First, we have to specify encapsulation type on these interfaces. We have 2 options here, except the negotiate, which is by default. We have .1q, which is open standard, and ISL, inter-switch link. It's a Cisco proprietary type of encapsulation over trunk interfaces. We're going to use .1q because this is an open standard. And we will also use switch port mode trunk. And also, I'm going to replicate these right away on the switch 7. As you can see, interfaces on other switches have been reset because they noticed some other traffic through them. For example, 802.1q BPDU frames for non-default VLAN or VLANs. But let's do it manually. Switch port, trunk, encapsulation, .1q, switch port, mode trunk. As soon as we have configured, I have configured these commands, we see that there were some events on the access layer switches. Okay, so on switch 5 we see that interface Ethernet 0/0 undergone reset, as well as Ethernet 0/1. So let's check show int trunk their status, their trunking status. Okay, we see that the dynamic trunking protocol mode is auto, encapsulation negotiated 802.1q, and status is trunking. Okay, with native VLAN number 1, native VLAN is the VLAN for which frames are not tagged in the trunking connection or in the trunk. Okay, so let's see, let's take packet capture probably. For example, on Ethernet 0/0 of switch 1. Ethernet, Ethernet 0/0 on switch 1, okay? So, waiting for the console to show up with Wireshark utility. Okay. Now it's taking time. Let's wait a bit. Yes, Ethernet. Okay. So what we can see here is we can see dynamic trunking protocol, right? DTP. Oh, let's let the window refresh. Okay, waiting for response. Yeah. So let's click on dynamic trunking protocol message. Where is it? This is CDP. Yeah, dynamic trunk protocol. Yeah, DTP, operating administrative trunk auto. We can see that devices exchange dynamic trunking protocol messages. Well, primarily these messages are sent by the distribution layer switches because, as I said, the ports are assigned the DTP mode of dynamic auto, which means that the interfaces are kind of passive and do not send out the DTP messages on a periodical basis. But switch 6 and switch 7 have been configured with switch port mode trunk, and these enabled them to send out these DTP messages. Trunk status, value, trunk operating status, trunk administrative status auto, and trunk type, value 802.1q negotiated, and the sender ID is this one, type, and the value is the MAC address of the sender, AABBCC000100. Let's check. Let's check here. For example, we're going to check do show spanning tree, right? Okay, so this is 0B. Who is 0? Aha, 01 is basically the switch 1, right? Let's check. Show spanning tree. And yes, this switch 1 is the one that sent out this message. That's why we see here administrative trunking status auto. Let's find some other message maybe. CDP message. Okay, let's filter out by not CDP, DTP. DTP. There is some delay in displaying. The typed message. Okay, typed filter. Now let me find it. Just yeah, this one. 0B is switch 6. Zero B is switch 6. Okay, let's check what it has to offer. So trunking operating type is 802.1q. Trunk administrative type 802.1q. This was configured manually by using command switch port trunk encapsulation. And trunk administrative status on. I have configured switch port mode trunk command, which means I manually set the trunking mode to on. So this switch advertises the trunking mode as on, manually configured, and trunk operating status as trunk. That's why we do not need to configure switch 1. Because it was auto-configured due to dynamic trunking protocol operation. But let's configure additional commands here, namely switch port no negotiate. We freeze our config and operational status of these interfaces to be switch port mode trunk. Let's see what we have here, what we get here. It must take some time to respond to this config. And let's do this on the other switch. Switch port, no negotiate. Okay, what we see here, let us start new capture. Continue without saving. And this is going to be let me start all over. Capture and Ethernet 0/0. Let's see what about dynamic trunking protocol messages in this case. Well, configuring switch port no negotiate means that I effectively disabled the DTP protocol on the downlinks of distribution layer switches. So let's check it. And so far I don't see any dynamic trunking protocol messages here in the packet capture file or live capture. Okay. There's only one Let's see. But this one has been sent by switch 1, not switch 6 or switch 7. And you can see that switch 1 continues sending these dynamic trunking protocol messages. Let's see what it tries to achieve. Trunk status, value trunk auto, trunk type, 802.1q negotiated. Well, it sends out DTP messages, but it doesn't receive any messages because dynamic trunking protocol has been disabled on the distribution layer switches. Let's go back to the consoles of our switches and what we can see here. Okay, show interface trunk. There are trunking interfaces still. Switch port now negotiate, switch port now negotiate. Let me copy configuration to the non-volatile access, non-volatile memory. And the RAM. Okay, about trunks. So it took some few minutes to react to this situation, and the switch 1 disabled its own trunking interfaces. As you can see, we have syslog messages stating that first, 802.1q BPDU received a non-trunk interface Ethernet 0/0. So Ethernet 0/0 as well as Ethernet 0/1 has lost its trunking status, and the port is blocking because of inconsistent Ethernet, inconsistent port type. Let us check show spanning tree interface Ethernet 0/0, and indeed we can see that the port role is designated, but the status is broken and the type is inconsistent type. Well, it's because we haven't configured yet the switch port mode trunk, encapsulation, and no negotiate commands. So let's do this. So interface range Ethernet 0/0-1 switch port encapsulation trunk encapsulation.1q switch port mode trunk and switch port no negotiate. And these commands I'm going to replicate to all other access layer switches. So basically, let me write memory and do show history. These commands I'm going to replicate. Conf T, you can see that all other access switches have disabled their trunk ports because they ceased to hear the DTP messages from distribution layer switches. So let's configure now these switches as static mode trunk with no negotiation. Switch 3 the same. Okay, switch 4 and switch 5. Now, forgot to paste. Now all the switches have been configured with trunking mode for the first two interfaces. Let's check. Show interface trunk. Yes, show interface trunk. And we can see that trunks are back. Also here, we do not see any new DTP messages because we configured switch port no negotiate command. Effectively, I have disabled the dynamic trunking protocol on the interfaces. Okay, let's check spanning trees. And we see that apart from VLAN 1, we have spanning tree instances for VLAN number 5, 10, and 11. And so for all the VLANs, we can see that the root bridge is seen through the Ethernet 0/0 port of switch 2. But which one is the switch? The root bridge? Well, we can see that the root bridge is effectively switch 1 because it has AABBCC 000100. Let's check it. Show spanning tree, and this bridge has this address, base address. So basically, for VLANs other than 1, we have root bridge equal to switch 1, which is not good because switch 1 is the access layer switch. So let's reconfigure this. Let's configure switch 6 and switch 7 to be the root bridge and backup root bridge for all the VLANs that we have configured in our domain. Okay, we're going to configure first switch 6, and we have command spanning tree VLAN, then set of VLANs, and command priority, and the priority of bridge. Priority 0 is the absolute minimum priority. So now switch 6 is going to be the root bridge for VLANs number 5 and 6. And let's check it right away. Show spanning tree VLAN 5. Show spanning tree VLAN 5. You can see that the topology is being recalculated because the port is in learning state, and the root port is Ethernet 0/0, but the root bridge is switch 6 because switch 6 has this MAC address. Let's check it. Do show spanning tree VLAN 5. First, we can see that all interfaces on this switch in VLAN 5 are in designated role and forwarding status. And we can see that the root bridge MAC address equals to the local bridge MAC address, which confirms that switch 6 has become the root bridge for VLANs 1 and 5. Okay. Now let's configure backup route. For backup route, we must mention other set of VLANs, different set of VLANs, and different priority, namely 4096. So in case the root bridge for VLANs 10 and 11, which we are going to configure to be switch 7, goes down, this switch will assume root bridge role for these two VLANs. Now let's configure this switch 7. So spanning tree VLAN 10, 11, priority 0. This switch is going to be the root bridge for VLANs 10 and 11. And also, this switch is going to be backup root bridge for VLANs number 1 and 5 with priority 4096. Okay, let's save the configuration. And let's check For example, on switch 3. What are current topologies for these VLANs? Show spanning tree VLAN 5. Root port is Ethernet 0/0. What about VLAN 10? Root port is Ethernet 0/1. Show CDP neighbors. Ethernet 0/1 is connected to switch 7. So we have achieved layer 2 traffic engineering. For one VLANs, our active topology contains one set of interfaces. For the other set of VLANs, the other topology is calculated, so we are able to load balance traffic for different sets of VLANs. Now let's configure access ports. Let's start with switch 1. Conf T, interface range. Well, let's first check the show interface status. What ports do we have here? Okay, so we have two uplink ports, which are trunk interfaces. Let's configure these interfaces to be access ports. Interface range, Ethernet, okay, 1/0-3, Ethernet 2/0-3, Ethernet 3/0-3, and Ethernet 4/0-3. Okay, switch port mode access. Switch port access VLAN 1. I'm going to configure these interfaces explicitly into VLAN 1, although maybe even better option would be to first configure some auxiliary VLAN. For example, let it be VLAN number 99. Name empty. So just in case, let's configure our interfaces in VLAN 99. And also, I forgot to disable this VLAN with shutdown command. So this is kind of parking VLAN, which parks all unused ports. This is a measure against some automatic enabling ports in VLAN number 1. So even if someone connects to such port an active equipment or device, this port will not be forwarding any traffic because it is assigned to the VLAN, parking VLAN, which is shut down. So where's my interface range command? It's here. So switch port access VLAN 99. Okay, fine. Let's check our configuration. Show spanning tree VLAN 99. There is no spanning tree instance because VLAN 99 is a parking VLAN and it is disabled with shutdown command. Now, show VLAN ID 99. And we can see that this VLAN contains basically all ports, including trunk ports. Let's check. Show interface trunk. So this VLAN is automatically allowed in this trunk, right? Although there is no spanning tree instance for this VLAN, so basically it's not forwarded through the trunk segments. But as you can see here, VLAN 99 contains, it's locally shut, but contains all local ports, including both trunk ports. Okay, let's replicate this config on the other switches. Yeah, okay. I will do manual configuration on switch 2. VLAN 99, name empty, and shut down, and Then interface range. Okay. We can jump from one configuration mode to some other configuration mode directly. Switch port mode access and switch port access VLAN 99. Okay, the config is saved. So now here I can get clear history of configuration commands and can just copy paste everything this. Okay. And switch 5, the last access switch. Okay, so let's check our config. We have VLAN 99 in shutdown state. We do not see config of other VLANs because the VLAN information is stored on NVRAM and in a separate file called VLAN.dat. Okay, we can see that the ports that are denoted as access ports are set to VLAN 99. And we have already seen that there is no spanning tree for VLAN 99 as VLAN 99 has been shut down. Okay, so I'm going to stop at this point because the video has become too long, and see you in the next videos. Bye.